Welcome to our video about solving right triangles. To solve a triangle means to find all of the missing side lengths and missing angles. Of course, there are 6 total, 3 side lengths and 3 angles in all triangles. But we, of course, are given some information to start, so we won't have to find 6 total things. If you take a look just at this first example here, we're given, of course, that there is a right angle, we're given one of the acute angles, and we're given a side length. Therefore, we have 3 remaining pieces to find: a missing angle, a side length, and the hypotenuse. We can also see that this triangle has an angle measured in degrees. Therefore, for this video, you need to make sure that your calculator is in degree mode. In order to solve right triangles, we are going to use trigonometry, SOHCAHTOA specifically. We are also going to use some geometry ideas, one of them being that the 3 angles inside a triangle always sum to 180 degrees. We also have the information that the Pythagorean theorem gives us. If we know 2 side lengths, whichever 2, of a right triangle, we can also use the Pythagorean theorem to find the remaining 1. So these 3 things over here, and I'm sure there's a few more along the way, but these 3 things here are our methods for solving right triangles. Now, specifically right triangles, we can only use the Pythagorean theorem with a right triangle, and we can only use the sine, cosine, and tangent in the way that we will be using it today for a right triangle. However, all triangles, no matter what type, their 3 interior angles sum to 180 degrees. So this is not specifically just for right triangles. Let's use these 3 pieces of information in order to solve this first triangle here. The first thing that I'd like to focus on finding is our missing angle. This is the Greek letter alpha. We know that all 3 angles do sum to 180 degrees, but with a right triangle we have even a cooler shortcut. Since this angle is 90, that means these other 2 acute angles have to add up to 90. Therefore, we can simply find this angle alpha by doing 90 minus 34. Therefore, our other acute angle that was missing, alpha, is 56 degrees. I went ahead and labeled it here so we can use this 56 degrees potentially to find other missing pieces. Next, let's focus our attention on one of the missing side lengths. I'm going to start with finding the side length B. Now, we can find B in a couple different ways. We cannot use the Pythagorean theorem yet because we only know information about 1 of the side lengths, and in order to use the Pythagorean theorem, we need to know 2 of the side lengths of the 3 to find the missing 1. So we do have to use SO, CA, or TOA. Now, which one we use kind of depends on your perspective, what information you have, and really just your preference. I'm going to use 34 degrees and this 12 right here, and then, of course, B. So if we're looking at the side length B from the perspective of being at 34 degrees, we would say that the side length B is the opposite side. Then 12 is the adjacent side to the 34 degrees. Because we're going to be dealing with 34 degrees, we have opposite and adjacent. That is tangent. The tangent of an angle is the opposite side divided by the adjacent side, or TOA. To find B, therefore, I'm going to use a tangent. We set it up like this. We say that the tangent of our angle, 34 degrees, equals OA, O over A, opposite over adjacent. So B over 12. Now from here, we can see that we can multiply both sides by 12 to solve for B, or what I prefer is to put this over 1 and then to cross multiply. The reason I do that is because sometimes our variable that we're looking to find might be in the denominator. So this is like a surefire way to make sure that we get what we need. So when we cross multiply, we'll get 1b equals 12 times the tangent of 34, what we would have gotten anyway if we multiplied both sides by 12. Now here's where our calculator comes into play. Of course, we're dealing with degrees, so we do have to make sure that our calculator is in degree mode. From here, I'm going to just plug this into my calculator. 12 times, use the tan button, put in 34, close the parentheses, and hit enter. you should get 8.094, and then the decimals do go on. Let's round to the nearest tenth, so we'll have 8.1. So B is approximately, because we are rounding a bit, 8.1. Now does this make sense? You might recall back from geometry or algebra 2, or maybe not at all, that the larger the angle is, and if you look at what it opens towards, so this angle here that's 56 degrees is going to open to a longer side than its smaller angle 34 is going to open up to. It's sort of like opening a door. If you open a door a little bit, you're not really able to get through because the side that's across from it is very small. Whereas if you open a door a lot and that angle is very big, then you're able to get through the doorway because the side length that you've created is big. So 34 is smaller than 56, therefore the side length across from 34, 8.1, should be smaller than the side length across from 56 degrees, which is 12. So it does make sense. Now, the last thing that we need to do in order to solve this right triangle is to find the hypotenuse C. There are two ways that we can do this. Can you think of two ways? The first way is that we could do already kind of what we just did. We could do so or ka. In this case, because we wouldn't use tangent because tangent does not deal with hypotenuse. We could do the sine with 34 and it would involve 8.1 in C, opposite in hypotenuse. We could do the cosine with 34 and it would involve adjacent in hypotenuse, or 12 in C. So we can use trigonometry to find the hypotenuse C. We can also use the Pythagorean theorem. Now I'm going to do both of those just to see if we get answers that are a little bit off because of rounding. Now I do recommend, if you use trigonometry here, use the side length of 12 and not 8.1 because the 8.1 already has some rounding built in. So I'm going to use, we can use either the 56 or the 34. Those are not rounded values, but I'll use the 34 again. Let's use 12 and C from the 34-degree angle. From our 34-degree angle perspective, 12 is the adjacent side length and C is the hypotenuse. Out of SO, CA, and TOA, which one deals with the adjacent and the hypotenuse? That's cosine. So we have that the cosine of 34 degrees equals our adjacent 12 over our hypotenuse C. Now in this case, we are solving for C and the variables in the denominator. So once again, I'm going to put the cosine of 34 over 1, and I'm going to cross multiply. So we'll get C times the cosine of 34 degrees equals 12 times 1, or just 12. Then we'll divide both sides by the cosine of 34. And that is exactly what we put in our calculator. So C equals 12 divided by the cosine of 34. Let's see what we get. We end up getting 14.474615 ... Rounding to the nearest tenth, which is what we've been doing, we'll get 14.5. All right, so we have found C using one method. We used trig. Next, let's find C using a different method, the Pythagorean theorem, and see if we do in fact get 14.5. We're going to take 12 squared plus 8.1 squared equals C squared. When we add 12 squared plus 8.1 squared together, we end up getting 209.61. Then of course we have to take the square root to find C. We do in fact once again get 14.47, and in this case it's 4779. So it's a little bit different, but not different enough to really matter when we're rounding to the nearest tenth. So it looks like rounding to the nearest tenth is okay, and it shouldn't throw off our final answers too much. So we ended up finding C is 14.5, and we solved our right triangle using trigonometry with SOHCAHTOA, the fact that the angles inside any triangle sum to 180, and specifically in a right triangle, the two acute angles sum to 90, just a little shortcut. And then finally, we also used the Pythagorean theorem. Of course, we didn't need to use the Pythagorean theorem, but if that's something that you like to use, it's definitely a tool in your toolkit for solving right triangles. Our next problem will be a you try problem. So go ahead and get this drawn out in your notes and do your best to find the 3 missing parts to solve the triangle. Hit pause right now and then hit play when you're ready to see the solutions. And here are the solutions. In order to find theta, which is the first thing I usually do, realize 47 and theta have to add up to 90. So in order to find theta, we can just do 90 minus 47, and we'll get that that angle's 43. Of course, 90, 43, and 47 do sum to 180. Then I tackled finding A. Now, you could have found A in a different way. If you found that it's 5.6, then you did it correctly. That's the idea. You could have used the tangent of 47 equals 6 over A. I chose to do the tangent of 43 is A over 6. It's all about perspective, because whichever angle we choose, whichever acute angle, the opposite and the adjacent are swapped. So it is all about perspective with the SOHCAHTOA trig functions. So we end up finding that A is 5.6. Then, in order to find C, the hypotenuse, which you might have even done first, either way, could have used the Pythagorean theorem or trig. I chose to use trig, and I chose to use the 6 because it did not involve a rounded value. So I said the cosine of 43 degrees is the adjacent 6 divided by the hypotenuse 6. Then I cross-multiplied, this is cosine 43 over 1, and then found that C is approximately 8.2. If you'd like to use the Pythagorean theorem to double check that 6 squared plus 5.6 squared does in fact equal what 8.2 squared is, feel free. I did double check and these 3 values work. In this next example, we are not given anything drawn out, but let's draw out our own right triangle based on the information. We're supposing that theta is an acute angle in a right triangle. Then we are letting theta be 15 degrees, and the hypotenuse is a length of 10. We need to find out how long is the side opposite of theta. Let's first sketch a right triangle and label it appropriately. That is a decent right triangle. There's our right angle. I'm going to let theta equal this guy down here since it just looks like the smaller of the 2 angles. So that's 15 degrees. Then we know that the hypotenuse has a length of 10. All right, what do we need to find? We want to know how long is the side opposite theta. So we need to know what is this side length over here. I'll call it A. This is the side length opposite of theta, which is 15 degrees. We really don't need to know any more information other than these 3 things. We can just use a trig function in order to figure out what A is. From our 15-degree standpoint here, A is the opposite side and 10 is the hypotenuse, and out of SO, CA, and TOA, sine deals with opposite over hypotenuse. So we're going to use sine to solve for A. We'll have that the sine of 15 degrees equals the opposite A over the hypotenuse 10. Now please realize I'm not using A as like adjacent or anyway. I didn't mean to, I just chose A at random as a variable. I realize that it is the opposite side. I guess I could have chose O, but A it is. Then all we need to do is cross multiply. So we'll have that A equals 10 times the sine of 15 degrees. We end up getting, rounding to the nearest tenth, 2.6 units. Now this makes sense. It's going to be a pretty short side because this angle is very small, 15 degrees. So if the hypotenuse is 10, it clearly needs to be less than 10, but it's going to be a lot less than 10. This angle over here is 75 degrees, and it would open up to a side length much longer than this side length over here. Of course, this side length would also be less than 10, just because the hypotenuse is the longest side on a triangle, on a right triangle. But this side is definitely going to be pretty small. So you can kind of use that number sense to gauge if your answer seems correct or not. We found our answer. That's all we need to do is find one piece of information on the triangle. We did not have to solve the whole thing. Next up, we're going to take a look at some vocabulary that can help us with solving word problems and real-life applicable problems using trigonometry. Let's take a look at these different types of angles that can be used to describe angles in a situation. The first one is called the angle of elevation, or sometimes known as the angle of inclination. It is going up. So we have some baseline here. More often than not, the baseline is like just the ground level. Sometimes it is somebody's eyesight, so their head might be here, and their baseline might be eye level, it's usually one of those two things, and something or someone is looking up, and the angle going up towards that object is called the angle of elevation or inclination. Then we also have what's called the angle of depression, and no, it's not sad, but it's just going down, so it's just a little down. We have some horizontal line up here, and the observer is now looking down from usually their eyesight up here, they're looking down. So the angle of depression is going down from the top, looking down at the object. So those are the two different angles that may be described in some problems that we will be seeing here shortly. In this problem, we do have an angle of inclination. The angle of inclination from a point on the ground 30 feet away to the top of Lakeland's Armington Clock Tower is 60 degrees. Find the height of the clock tower to the nearest foot. First thing we got to do is draw it out. So we have some angle of inclination, so we know that there's a baseline, let's say it's the ground, and then we look up, 60 degrees going up, and we see the top of some clock tower. So the first thing I'm going to do is draw a clock tower. There is the most beautiful clock tower I've ever seen. All right, so we know that there is a point on the ground 30 feet away from the start of this angle of inclination. So it's like we're looking and we're looking up at it, but this length, we're 30 feet away from the base of the clock tower. So I'm going to draw that out too. So we have some horizontal bottom part here, and this is 30 feet. So I'm just going to put 30. Then we know that our angle of inclination looking up to the top of the clock tower, this is 60 degrees. What are we asked to find? We're asked to find the height of the clock tower to the nearest foot. Now I'm actually going to redraw it to the very top of the clock tower instead. There we go. Because we want to know the height. So I'm going to call the height of the clock tower H. We know we have a right angle. So we can really, once we've drawn it out, that's really the hardest part. We can now just use trigonometry in order to find the height of the clock tower. Now you also notice that this is a 30, 60, 90 right triangle. And so therefore we do also have those relationships between the side lengths. So if you remember those, you can easily know what what H is based on 30. However, you do not need to remember those things to use this trig. So we have 60 degrees, and from the perspective of 60 degrees, we have the opposite and we have the adjacent side lengths. So out of SO, CA, and TOA, we're going to be using TOA because it's tangent equals opposite over adjacent. I realize sometimes that just saying them might not be as helpful, so go ahead and write out SOCA TOA, then you can clearly see that the tangent is what we're using here because we have the opposite side length, H, what we're looking for, and we're given information about the adjacent, 30. Therefore, we know that the tangent of 60 degrees equals the opposite side, H, over the adjacent side, 30. Then when we cross multiply, we'll have that 1H equals 30 times the tan of 60. Plugging this into our calculator gives us 51.96. So, and actually we want to the nearest foot anyway. So the nearest foot is just the nearest whole number. So H is approximately 52 feet. I mentioned before there's a special relationship between the three side lengths of a 30, 60, 90 degree right triangle, and that is this is the shortest side because it's across from the smallest angle, 30 degrees, and this side is also 30. This side length right here, the other leg, would be this side length times root 3. So it's 30 times root 3, which is also this value here, about 51.96. However, we did not need to know that in order to use our SOHCAHTOA trig to find our solution. This next word problem is a little bit more difficult because it involves two triangles. So let's take a look at it and read it. In order to determine the height of a California redwood tree, two sightings from the ground, one 200 feet directly behind the other, are made. If the angles of inclination were 45 degrees and 30 degrees respectively, how tall is the tree to the nearest foot? So once again, we want to find the height of something. Let's start off by just drawing that first triangle. So we know we have to have a tree, and that is the height of the right triangle. Here's our tree. We know that we have some sighting from it on the ground, and that angle of inclination looking up to the top of the tree is 45 degrees. And we know that since there's two sightings on the ground, it says one's 200 feet directly behind the other. So we do not know the length of this first one. I'm going to call it X when we sketch it out. So we have this length is X, and looking up to the top of the tree, so there we go, right here. Then this is 45 degrees, that angle of inclination. And here is our right angle. Now we know we're looking for the height of the tree, so I'm going to call this H over here. Now we do have another triangle. It says that there's two sightings from the ground. One's 200 feet directly behind the other. So this is our first sighting. Then we know that we have another one that's 200 feet behind it, and that angle of inclination is 30 degrees. So let's sketch that out, adding on a little bit in yellow. So we know that this extra is 200 from here to here. And then this angle of inclination to the top of the tree was 30 degrees. The only other thing that I can think about writing in is that we know that this entire length of the overall triangle is 200 plus x. So I know that it's both together if we look at it as one big triangle instead. Here's the problem though, is that we have two different variables. However, there is a way in order to not have two different variables anymore. We can use this original 45, 45, 90 right triangle in order to see that x and h are the same length. That's because in a 45, 45, 90, it's an isosceles triangle. Therefore, these two side lengths are the same. If you did not see that, we can use trig. We do know, if we're just looking at this original white triangle here, we see that we have 45 degrees, we have the opposite and the adjacent side lengths. Therefore, we can use tangent with them. So we'd have the tangent of 45 degrees equals the opposite h over x, the adjacent. The tangent of 45 degrees is 1. So we know that 1 equals h over x. That means when we divide h by x, we get 1. H and x have to be the same. You can see that too if you multiplied both sides by x. You have that they're the same length. So I am simply going to call h x instead because we know that they're the same thing. So in our drawing, we know that what we're really looking for is x because that's the height of the tree. Now that helps us a little bit because now we're down to just this being all in terms of one variable instead of being in terms of multiple variables. Let's see if we can use our larger triangle, one that is both yellow and white, this 30, 60, 90 triangle, to find x. From 30 degrees, we have the opposite x and we have the adjacent side length here, which is 200 plus x. We once again are going to use tangent. So we have that the tangent of 30 degrees equals the opposite, x, over the adjacent, which is 200 plus x. Now, from our studies on the unit circle, we might see that we know that the tangent of 30 degrees is root 3. If you want to replace tan 30 with root 3, feel free. If not, I would recommend not using the decimal approximation just yet and keeping it as tan 30. So it's up to you. If you'd like to call that root 3 because we know that's what it equals, feel free. From this point, I'm just going to attempt to solve for x by cross multiplying. So we'll have x times 1, which is x. And then on this side, we do have to make sure that we multiply the tan 30 all the way through the 200 plus x. So we'll have 200 tan 30 plus x tan 30. Then we want to get all of our terms with x on the same side so we can factor it out and solve for it. We'll do this by subtracting x tan 30 from both sides. Now, all of our terms with x are on the left-hand side. We can factor the x out, so we're left with 1 minus tan 30 equals 200 tan 30. From this point, we can divide both sides by 1 minus tan 30. Now, when you do this in your calculator, you do need to make sure that when you're dividing by more than one term here, it definitely needs to be in parentheses. So be careful and check to see that you get the same solution. Doing that in our calculator, we should get x is approximately 273.205. The directions do ask how tall is the tree to the nearest foot. Therefore, our final answer is 273 feet. That's a tall redwood tree. Here's our last example, and definitely the most challenging. We have from the observation deck of a lighthouse at Sasquatch Point, 50 feet above the surface of the lake. A lifeguard spots a boat out on the lake sailing directly towards the lighthouse. The first sighting had an angle of depression, so we're going down from the lifeguard. And the second sighting had an angle of depression of 25.9 degrees. How far had the boat traveled between the sightings? Let's sketch this out a little bit more than what I have already done here. So we have our lifeguard at the top of this lighthouse on the observation deck, and we have the horizontal line of sight and then like looking down. Now, just to keep it simple, I'm going to do like the line of sight right here. It doesn't really matter as long as it's consistent. But so remember, the angle of depression is we go out, but then start to look down. So an angle of depression of 8.2 is very, very slight. Like an 8.2 degree angle is pretty small. So let's try to sketch that first. So we have this horizontal, and then we have an 8.2 degree angle until we hit the water. Now I haven't drawn the water. That looks about right. So let's do the water like right here. Yeah, it's like on land here and then the water's behind it. That's okay. I'm not the world's greatest artist, but we're getting there. Okay, so this is where the boat first is. So this is boat sighting number 1. I'm not going to try to draw a boat, but here it is at this point. What do we know? We know that this angle right here is 8.2 degrees. We also know that we have 50 feet above the surface of the lake, which is right here. So this length right here is 50. And we, of course, have a right triangle. Now, we also are going to have another sighting, and the angle of depression is bigger. That's because the boat is coming towards the lighthouse. So it's going to be like 25.9 degrees. So it's going to be bigger and come down sooner. The boat has traveled. So at this point right now, the boat is this distance away from the lighthouse or the observation deck. So we really want to first find this length right here. Let's do that first without even finding or drawing the other triangle in to make it look messy. Let's just find this length here. I will call this length A. In order to find it, we see we have 8.2. We have information about the opposite and the adjacent, A. So we're going to use tangent. So of the tan of 8.2 degrees equals 50, which is the opposite, divided by A. Solving for A will give us 50 divided by tan of 8.2, which is 346.97. So I'm just going to leave it at 0.9 for now. So that's what A is. So I'm going to label A with 346.9. Next, let's use a different color in order to draw what's happening next. So we have another angle. This time our angle of depression is 25.9, so it's clearly going to be bigger. So this is where the boat is now seen for a second time. And we know that this angle all in here is the 25.9 degree angle. So once again, we have a right triangle. This one's now just orange. And we want to find the same thing. The distance that the boat is from this observation deck is going to be represented by this length right here. So we need to find it again in a very similar way. We're going to have the tangent, because, we also know that this is still 50. That hasn't changed. We know that the tangent of 25.9 is going to be 50 over the length we want to find. I'll call that length B. So we'll have the tangent of 25.9 degrees equals 50 divided by B. Using our calculator, we'll find that B is approximately 102.97. So I'll keep it at 0.9. So the question is asking us how far had the boat traveled between the two sightings. Well, between the two sightings is right here. If the entire length is 346.9 and the length that we don't want, because we only want this part of it, is 102.9, we simply need to subtract 346.9 minus 102.9 to get just this distance in between here. So our distance, this distance right here between the two boat sightings, we subtract and we get 244. Then we can see that the units in this problem are in feet, so our final answer is 244 feet in between the two boat sightings.